Hey there, welcome back everybody. In this section we're going to work with radical numbers and rational exponents. That's kind of a mouthful, so let's do a little bit of review here. So what is the difference between a rational number and a radical number? Those two things sound a lot alike, but they are very different. You might remember from our work with number sets that a rational number, remember the root word is ratio in there, rational numbers are numbers that are fractions. Whereas numbers that are radicals are roots. So we're going to work with roots and numbers that have rational exponents in them because they're closely related. So let's take a look. Okay, so let's start by taking a look at the fundamental relationship of the day, and that is the definition of x to the 1 over n power. We define x to the 1 over n power as being a root. So x to the 1 over n power is the same as the nth root. So you can see here that 8 to the 1/3 power is equal to the cube root of 8, which is equal to 2. And that allows you to evaluate roots without having to use a root symbol. We can just express them as exponents. So let's take a look at these three examples. So our first one, 9 to the 1/2 power. Since our bottom number in this fraction is 2, that's the same as saying the second root of 9. But of course the second root of 9 is really just the same as the square root of 9, and so 9 to the 1/2 power is 3. Our second one, negative 64 to the 1/3 power. Well, there our bottom number is 3, so that's the same as saying the cube root of negative 64. Note that that negative sign is inside the parentheses, and therefore when it becomes a root, it goes inside the root. Now the cube root of negative 64, what number times itself 3 times will give you negative 64? Well, we know it has to be a negative, and the cube root of 64 is 4, so that turns out to be negative 4. Now it's worth noting that you should be able to type these into your calculator as well, and I'd recommend you do that. Take your calculator and type negative 64, use some parentheses, and raise that to the 1/3 power. You might need even to put parentheses around the exponents of 1/3, and you should get the same result, negative 4. Now our third one, 16 to the 1/4 power. That's just another way of expressing the fourth root of 16. Now again, you could type that into your calculator or that into your calculator. On most calculators, it's easier to type in a fractional exponent than it is to dig through your menu to find out what the value of a fourth or fifth root is. And of course, the number times itself 4 times that give you 16. That is 2. I want you to pause the video for just a minute and see if you can do D. What is negative 1/32 to the 1/5 power? Unpause when you're ready to see that solution. Okay, well, negative 1 over 32 to the 1/5 power, easy enough to recognize that that's got to be a fifth root since it's 1/5 power, and it must be the fifth root of 1 over 32. Notice that the negative sign was outside the parentheses here compared to our early one where it was inside. That means our negative sign stays out in front of the root instead of inside. Now in this case it wouldn't matter, but in some later cases it will, so watch the location of that negative sign. And so we can then break that up. The fifth root of 1 up in the numerator is 1, and the fifth root of 32 in the denominator is a 2, and so that becomes negative 1/2. Note that we can, when we have the root of a fraction, we can apply that root to the numerator and the denominator separately. That's one of the properties of radicals. Okay, we can expand that idea just a bit by defining x to the m over n as being the same as 1 over n, except m, our top number in our fraction or in our rational exponent, becomes the new exponent on our root. So x to the m over n, that's the same as the nth root of x, like we just saw, raised to the mth power, or we can put the m on the x first. Here's an easier example to see though. 8 to the 2/3, that's the same as the cube root of 8, as we saw just a minute ago. The denominator tells you the type of index you have, whereas the numerator gives you the power or the exponent. So that's the cube root of 8 squared. So we should take that one a step further though. 8 to the 2/3, as we just saw, that's the same as the cube root of 8, which we're then going to turn around and square. but the cube root of 8 is just 2. So when we square that, we end up with a value of 4. Now you could have worked that in the opposite direction as well. We could have said 8 to the 2/3 power. That's the same as the cube root of 8, and instead of squaring it after we get the root, we could square it before we get the root. That becomes the cube root of 8 squared, which is the cube root of 64, which is, of course, 4. So we're going to get the same result. We're just taking a little bit different path to get there. Let's look at these examples. 32 to the 2/5 power. That's the same as the 5th root of 32, but then when we're done, we'll take that value and square it. Well, the 5th root of 32, that is 2, which we're going to square, and we get another value of 4. 81 to the 3/4. Well, our bottom number gives us our index, so that's the 4th root of 81, but then we're going to take that value and cube it. So the 4th root of 81, that's 3, which we're then going to cube. That turns out to be 27. One more here. Negative 64 to the 2/3 power. Again, you could type that right in your calculator, and I'd recommend you try that, but we don't need the calculator to do it. That turns out to be the cube root of negative 64, but that value is then going to be squared. Now we already saw that the cube root of negative 64, that is negative 4, and we're going to square that. This turns out to be 16. I want you to take a minute, pause the video, and do D there, negative 1/25 to the 3/2, and unpause when you're ready to see that solution. Okay, negative 1/25 to the 3/2 power. That's the same as, now our negative sign is just going to stay out in front of the whole thing here. That's going to be the square root, or if you wanted to put that 2 on there, you can, the second root of 1/25, but that's going to be cubed with a negative sign out in front of the whole thing. If we take that a little bit further, the second root of 1/25, or the square root of 1/25, well, the square root of 1 is 1, and the square root of 25 is 5. Now that's going to get cubed. The negative sign still waits out in front. Okay, 1/5 to the 3rd power. That's the same as 1 cubed over 5 cubed. 1 over 1/25. Negative sign is still just waiting out in front. You should end up with negative 1/125. Okay, and our last fundamental definition here is the definition of x to the negative mn. As we saw in our properties of exponents just a lesson or two ago, a negative exponent means reciprocal. So that means that x to the negative mn, that's the same as 1 over x to the mn. That's really not a new property. We've seen that before. In other words, we can change a rational exponent to being positive by moving it to the other half of the fraction. If it's above, we move it down. If it's in the bottom, we move it up. Noting, of course, that our denominator can't be 0. Let's take a look at a few examples here. 64 to the negative 1/2, that's the same as 1 over 64 to the positive 1/2, which is, of course, the same as 1 over the second root of 64, or in other words, the square root of 64, which means this is 1 over 8. Try typing that into your calculator. 64 exponent negative 1/2, might need parentheses around that negative 1/2. You should get 1/8. Okay, negative 16 to the negative 5/4. Be careful here. Two different negative signs meaning completely different things in this number. The negative sign on the 16 means it's smaller than 0, whereas the negative sign in the exponent means reciprocal. So we can automatically make that exponent positive by saying that this is 1 over negative 16 to the positive 5/4 power. We can rewrite that as a root and say that it's 1 over the 4th root of negative 16, and then we're going to take that and raise it to the 5th power. But right here we have a problem. The 4th root of negative 16. We can't take an even root of a negative number. We can't take the square root or the 4th root or anything else. There's nothing raised to a 4th power that will give us negative 16. So as it turns out, that number is imaginary. So there is a number that still exists, but it's in the family of complex numbers, and that's beyond the scope of this course. So when that happens, we can stop and recognize that we have an imaginary number. If you're not sure, try typing that into your calculator and you'll get an error message because that is not a real number, and most calculators only deal with real numbers. Okay, our third one, negative 625 to the negative 3/4. Notice here that our negative sign is out in front of our number instead of inside with the parentheses. That makes a big difference. In our previous problem, the negative sign ended up inside the root, and that's why we got an imaginary number. That's not the case here, so we might have better luck. So we're going to rewrite this as negative, for the negative sign hanging out in front, 1 over, and that's because of the negative exponent, 625 to the positive 3/4 power, since we're putting it down on the bottom. Now we can go a little bit further with that. That's the same as negative 1 over the 4th root of 625, but that we're going to raise to the 3rd power. But we can go a little further with that. That's the same as negative 1 over the 4th root of 625, that is 5, which we're going to raise to the 3rd power. And that means this simplifies to negative 1 over 125. Let's do one more together, and I'll give you the last one for practice. We have negative 32x to the 5th. We have a variable here, and that's all raised to the negative 2/5 power. Well, that's the same as 1 over negative 32x to the 5th to the positive 2/5 power, since we've moved it to the denominator. And that's the same as 1 over the 5th root of negative 32x to the 5th, and then we're going to square that. That's the same as 1 over, let's see here, the 5th root of negative 32, that's negative 2. And the 5th root of x to the 5th, that's going to be x. So 1 over negative 2x, but we still need to square that. And this becomes 1 over 4x squared. Okay, pause the video, and I'd like you to figure out what the actual value of e, our last problem there, is. 1 over 25 to the negative 3/2. Okay, here we go. 1 over 25 to the negative 3/2. Now here, the negative exponent's in the denominator. We can send it back up to the top, and this just becomes 25 to the positive 3/2. Now, that we can rewrite as the square root of 25, in turn raised to the 3rd power, which is, of course, 5 to the 3rd power. And so that means that the value of this is 125. I hope you got that. If not, rewind that and watch that again and make sure that you understand where your mistake was made. Okay, well, we're going to continue to simplify expressions here, but it's relevant for us to review the basic properties of exponents that we have already seen in an earlier lesson. Of course, when you multiply like bases, you add the exponents. When you divide like bases, you subtract your exponents. When you have a power to a power, you multiply those exponents. Hopefully those three are familiar. We use those a lot. When we raise a product of two numbers to a power, each factor gets raised to that power. When you have some fraction raised to a power, both the numerator and the denominator get raised to that power. And of course, anything to the 0th power is 1, as long as we're not talking about 0 to the 0th power. Now you might think, wait a minute, there was 7 properties, and you're right, but the negative exponent property we've already worked with in this lesson, so I haven't listed that here. So let's see why that's useful to review. Let's take a look and simplify each of these expressions. We're going to do these together, and then I'll give you a few to do for practice in just a minute. Our first one, 5 to the 2/7 times 5 to the 3/7. Well, we know that like bases, we can add these exponents, and that becomes 5 to the 2/7 plus 3/7 is 5/7. And so we could leave it like that, or we can, since we now know how to handle that fractional exponent, we can say that that is the 7th root of 5, and then we're going to raise that to the 5th power. Now you certainly could do that on your calculator, but we'll leave it just like that. 5 to the 5/7, which is the same as the 7th root of 5 to the 5th power. Either of those are equally correct. Our second one here, 11 to the 2/7 cubed. Power to a power, we multiply those and we get 11 to the 6/7, which is certainly true and acceptable, or we can say that that is the 7th root of 11, all raised to the 6th power. That's another way to express the same thing. Our third one, a to the 2/3, b to the 1/2, all to the 6th power. That 6 is going to be applied to each of these individually, so it's a power to a power 2 different times. So a to the 2/3 times 6, well, 2/3 times 6 is 4. And b to the 1/2 to the 6, well, 1/2 times 6 is 3, and so that becomes a to the 4, b to the 3rd, and that's really all we can do there. And our last one, a to the 8/3, a to the 1/3 over a squared. First of all, in the numerator, we can add those fractions together. 8/3 plus 1/3 is 9/3, all over a squared. But of course, we know what a to the 9/3 is. 9/3 is just 3, so that's a cubed over a squared, and a cubed over a squared, those basically cancel off, leaving just a to the 3 minus 2, or a. Okay, these are a little bit trickier, but I think you should be able to handle these. Pause the video and simplify each one of these 3. If you can do these, you're in really good shape. Unpause when you're ready to see the solutions for these. Okay, well, there's more than one look to how you might simplify these, so you could do that a different way and still get the same result. That exponent of 1/2 gets applied to both of these things inside, so we're going to have 81 to the 1/2 times n. Now n to the 8 to the 1/2, we would multiply those exponents and get n to the 4th. So this is 81 to the 1/2 and n to the 8 to the 1/2, but that's n to the 4th. Now 81 to the 1/2, that of course is the same as the square root of 81 times n to the 4th, making sure that the n to the 4th is not inside the root, only the 81 is being raised to the 1/2 power there. But the square root of 81 is 9, so we get 9n to the 4th, and we're done. Okay, our second one, a lot of different ways we could approach this. One way is to just apply the negative 2/3 power to everything on the inside. That means we're going to have 8 to the negative 2/3. N to the negative 2 to the negative 2/3. We'll multiply those exponents and get n to the 4/3. M to the 6 to the negative 2/3, multiply those exponents to get m to the negative 4th. Now that's all over p to the 3rd to the negative 2/3. We'll multiply those exponents. 3 times negative 2/3 is going to be p to the negative 2, and r, negative 1 times negative 2/3 is going to be 2/3 power. Now these negative exponents we don't like, so we're going to move those around to make them positive. That means 8 to the negative 2/3, we're going to send that downstairs to become 8 to the positive 2/3. N to the 4/3, that's going to stay up on top. M to the negative 4, we'll send that down and make it m to the 4th. P to the negative 2, we'll move that up, it becomes p to the positive 2. And r to the 2/3 will stay right where it is. Now, 8 to the 2/3, we can do a little bit better than that. That's the cube root of 8 squared. We already saw that in an earlier example. Now, 8 to the 2/3, we already saw that that's the cube root of 8 squared. But the cube root of 8 is 2, and 2 squared will become 4. So when we simplify this, we have n to the 4/3 p squared over 4 m to the 4th r to the 2/3. Okay, for our last one, I'm going to take a little bit different approach. What does that negative exponent of 2/5 mean again? That negative sign means reciprocal, right? And so instead of applying this individually to all those terms, we can flip over the fraction inside parentheses, and by taking that reciprocal, by flipping it, we are making that a positive exponent. And so we can change this to become c to the 10th over 32 a to the 5th b to the negative second power. We flipped what's inside. We took the reciprocal, so now it's not negative 2/5, it's now positive 2/5. Now you wouldn't have to do it that way, but that's one way to deal with that negative exponent. Okay, let's keep going here. So c to the 10th to the 2/5. Let's multiply those exponents, and 10 times 2 is 20 divided by 5. That's c to the 4th over 32 to the 2/5. A to the 5th to the 2/5 power, we'll multiply those to get a squared. And b to the negative 2 raised to the 2/5, that's going to be b to the negative 4/5. Now we can do better than that, of course. That's going to be c to the 4th over 32 to the 2/5. That is the 5th root of 32, but we're going to turn around and square that. And a squared. Now b to the negative 4/5, let's send that up to the top to become b to the positive 4/5. And one more step and we're there. That leaves us with c to the 4th, b to the 4/5 over the cube root of 32, which is 2, squared, or 4a squared, and that one is simplified. There's a lot going on there. If you got that one, nice job. If not, go back in your work and find your error and learn from that so that it makes sense. Okay, just one more thing here to look at before we wrap up this topic. In order to multiply and simplify radicals, we need to just recognize one thing. First of all, there's something called the product rule for radicals that says that if you have the root of a product or a root of two things that are multiplied together, you can split them up into individual roots. And the opposite is also true. If you have two roots with the same index, you can multiply the radicands, the thing inside, together to form a single root. Now that only works if the radicand, the thing inside, our a and b here, are not negative, but that's no problem for the work we're going to do in this class. Also, we have to note that the indices have to be the same. We can multiply square roots or cube roots, but we can't multiply a third root by a fourth root, for example. But again, we're not going to be doing any of that. So let's look at these three cases on your screen and see how these get multiplied and then simplified. The first one, a, we're going to multiply the square root of 5 times the square root of 10. Now that says that the square root of 5 times the square root of 10, we can combine those and call that the square root of 50. Now we've turned it into a root, but here's the thing. The number 50 contains a perfect square. That is to say, we can break that back up into the square root of 25 times 2. Do you see the advantage of writing that as 25 times 2 instead of 5 times 10? Because you know what the square root of 25 is. That is to say, that is the square root of 25 times the square root of 2, which becomes 5 times the square root of 2. And you should be skeptical of anything I tell you, and so you can check that on your calculator. If you take the square root of 5, which is 2.23 and some change, times the square root of 10, you get 7.071. Now, if we multiply 5 times the square root of 2, we get the exact same thing. So it is certainly the same value, but this one is completely simplified. It's not simplified when it's the square root of 50. If there's a perfect square or some part of that radicand that can be simplified, like the square root of 25, we always want to do that. Let's take a look at another one. b, 3 times the square root of 6 multiplied by 2 times the square root of 3. Now notice here that the 3 and the 2 are coefficients. Those are not within the roots. Those we can combine and call a new factor of 6. But the roots, the square root of 6 times the square root of 3, those we can put together and call the square root of 18. And 18 has a perfect square in it. We can break that up into the square root of 9 times the square root of 2, since 9 times 2 is 18. Now that 6 still lives out in front. So 6 times root 18 becomes 6 times root 9 times root 2, but the square root of 9, that's 3. And so we can call this 6 times 3 square root of 2. But of course, 6 times 3 can be combined, and we end up with 18 times the square root of 2. And so there's our result. That is completely simplified. Negative 2 cube root of 7x times 6 cube root of 49x squared. Well, we can kind of do the same thing as we did in example B here. Negative 2 times 6, we can put those two together and make our new coefficient a negative 12. And this cube root of 7x can be combined with the cube root of 49x squared. See, those indices are the same. That's what allows us to do that. And we will end up with the cube root of 7 times 49, well, that's 343, but it's also 7 times 7 squared. We'll write that as 343. And x times x squared is x cubed. So we have negative 12 times, now the cube root of 343, we said that that was 7 times 7 times 7. So the cube root of 343 is 7. And of course, the cube root of x cubed is x. And so negative 12 times 7x, that's going to be negative 84x, and we have that completely simplified. So again, combine the coefficients by multiplication. We combined the roots because they were like indices, and all your work for today will have like indices, so you can do that, and then simplify the resulting root. Okay, I'd like you to take a shot at these two. Simplify each of those. If you can do that, you're in good shape. Unpause the video and we'll work through them. Okay, our first one, 5 root 14 times 2 root 8. Well, first of all, notice that 8 actually can be simplified before we do anything. We can rewrite that as 2 times square root 4 times the square root of 2. Now, you wouldn't have to do that, but if you recognize that that 8 has a perfect square in it, we can simplify that right off the bat. And so this becomes 2 times the square root of 4, which is 2, times the square root of 2. Now, let's take our 5 root 14, which hasn't changed, and we'll multiply that by our 2 times 2 square root 2. Okay, so our coefficients, we have 5 times 2 times 2. That's 5 times 4. Our new coefficient is 20. And our root will be root 14 times root 2. That's the square root of 28. Now, are there any perfect squares in that 28? Well, yeah, there are. That's the same as 20 times the square root of 4 times the square root of 7. But we know that 20 times the square root of 4, that's just 20 times 2 times the square root of 7, which is 40 square root of 7. And we've got that one done. Now, if you didn't spot that 8, you would have taken 8 times 14 and gotten 112. And the square root of 112 would have simplified down the same way. Okay, and our last problem of the day here. The cube root of 48 times the cube root of 54 divided by the cube root of 6. Well, two things to note here. First of all, notice that 48 can be broken up into 8 and 6. But 8 is important because that is 2 to the third. That is to say, we can take the cube root of 8. Also notice that 54 can be broken up into 27 and 2. And 27, kind of like 8, that's a perfect cube. That's 3 to the third. So if we break up these roots, we can simplify them. So let's rewrite the cube root of 48 as the cube root of 8 times 6. And let's write the cube root of 54 as the cube root of 27 times 2. Those are both still over the cube root of 6 for now. Now let's split that up. We can rewrite that as the cube root of 8 times the cube root of 6 times the cube root of 27 times the cube root of 2. And that's still all over the cube root of 6. Now, this thing will fall apart in a hurry. First of all, the cube root of 6 over the cube root of 6, those cancel completely. They're gone. That leaves us with the cube root of 8, which is, of course, 2. The cube root of 27, which is, of course, 3. And the cube root of 2, which we can't simplify. So those are the factors that survive here, which means we can rewrite that putting the 2 and 3 together. 2 times 3 is 6 times the cube root of 2, and that is the simplified expression. So if you got that one, great job. If not, you might want to rewind that explanation and make sure that you are able to simplify something like that. Okay, so to wrap that up, a couple of key points here. First of all, just remember that x to the 1 over n is the same as saying the nth root of a number. That x to the m over n is like saying the nth root to the mth power. And of course, a negative exponent still means that we take the reciprocal of that value. For simplifying, know that we can always combine roots of the same index and we can split them apart, and that allows us to simplify. Those key points are really the 4 tools that you're using in this whole lesson and in your homework. So as always, go ahead and work through those. Let me know if any of them give you trouble, and I'll certainly meet with you online or otherwise to help you make sense of all that. Good luck. We'll see you in the next lesson.